Welcome everybody. In this tutorial, I'm going to show you how to do a eigenvalue buckling analysis in ANSYS. It will be a pre-stress eigenvalue buckling analysis. So the first thing you'll do is when you get to your main menu is you'll go here and grab static structural and drag it to the green box. And then the next thing we're going to do is grab the eigenvalue buckling, and you're going to actually drag it down to where it says solution and then release the left click, and you'll see that you now have a static structural and an eigenvalue buckling menu box, and the solution from the static structural will be used to solve the eigenvalue buckling problem. Now I've already created the geometry here. It's a 2-inch cross-sectional square beam that's 60 inches long. So I'm going to drag the geometry over to here. And then the next thing I'm going to do is I'm going to change the material or add a new material. So I'm going to right click material, engineering data, click edit. I'm going to go here where it says click here to add new material and right click over it and click engineering data sources. And then I'm going to go to the general materials library, double click that. I'm going to use aluminum alloy. So I'm going to click the plus icon. I'm going to go back to the main menu, and I'm going to, just real quick, I'm going to make sure my units are in US units. So you go up here to units, and I'm going to change it to US engineering pound inches. And then I'm going to right click on model and click edit. And it takes a few seconds to load. All right, so first thing I'm going to do is make sure our units are correct. So yeah, I'm using inches. So you'll see over here in the model tree that you'll now have this tab called Eigenvalue Buckling, and then you'll have a static structural tab. So in order to run the Eigenvalue Buckling solution, it needs to know what your loading and your constraints are, because it's calculating the eigenvalues based on those loading conditions. And so I'm going to change the material from structural steel to aluminum. So I'll go down here and then click aluminum. And the next thing I'm going to do is I'm going to mesh the model. So I'm actually going to I'm going to do a sweep mesh. So I'll show you guys how to sweep mesh. So I'm going to right click, insert, sizing, and I'm going to click the face and click apply. And I'm going to make this mesh a 1/4 of an inch. And then the next thing is you'll right click mesh, insert, and then click method. And then make sure your body is selected. Click the part, click apply. And I'm going to change the method from automatic to sweep. And then I'm going to do a manual source target. So I'm going to click manual source and target. Now what this is going to do is I'm going to select the face that I want the source mesh to be based on, and then the opposite face for the target mesh. And I'm going to change this to all quad. And I've already done the math, so I want a 1/4" element all the way through the part, like in the length direction. So I'm going to change this to 240 divisions. And then I'm going to change the element order to quadratic and right click generate mesh. And there we have our mesh. So in order to run the buckling, like I said, you have to run, I'm doing a pre-stress eigenvalue buckling. So I have to run a static structural analysis here. So I'm going to set up my boundary conditions. Now I'm going to model this beam, try to model the boundary conditions as close to the boundary conditions that are used in the Euler beam theory. So I'm going to try to model the boundary conditions as basically a fixed support with 1 degree of freedom in the rotational direct orientation about the x-axis. So I'm going to right click. I'm going to do this with remote displacement. So I'm going to click remote displacement. I'll click the top face here, click apply, and then going to set the x translation to 0 or displacement to 0 and the z to 0. And then now in order to actually load this, instead of using a force, I'm going to apply a small displacement in the negative y direction. So I'm going to do 1 mil displacement in the y direction. And that is going to provide the loading, the axial loading for the buckling case. And the reason why I'm using this method is because I found that it replicates the boundary conditions for the Euler beam theory. And when we compare it to Hancock's, I'll talk a little bit more about it. But basically, you have to fix both ends. So this is the best way I found to provide a loading on it. So again, from Hooke's law, F equals kx. So if I load it in the y direction, I'll get a reaction force. If I load it down in the y direction, we'll get a reaction force in the positive y direction, and then I'll put this in compression. So then z, I'm going to set equal to 0. And I'm going to leave the rotation about the x-axis free because we're trying to model a loading case where this will be simulating a beam that's pinned on one end. So it needs to be able to rotate in about one axis. And then the next thing I'll do is set the boundary condition on the opposite end of the beam. And again, I'm going to use remote displacement for that. Click the bottom face and click apply. And then these are x and y will be 0 because it's fixed. And z will be 0. We're going to leave the rotation about the x-axis free. And then rotation about z is 0. Now I'm going to add in some stress uh, post-processing metrics here, max principal, and we'll look at the stress in the normal direction, the y normal direction, and then I'm also going to add a probe. So in order to add these, I'm right-clicking solution, insert, probe, and force reaction, and we'll do it about the remote displacement on the bottom. And the reason why I'm doing this is because I'm going to use the results from the eigenvalue buckling results will give you the first mode as a function of the load factor. So what I'm going to do is multiply the load factor by the force reaction to get our critical load for that mode. So I'm going to right click solve. Okay, and it's solved. And our normal stress should be, we'll take the reaction load and divide it by the cross-sectional area, and that should be our normal stress. So the force reaction is 686.52. And if we just verify our stress, cross-sectional area is 4. It's a 2 by 2, so it's 4 inches. And 71.63. And that's what we're getting. Okay, so the next thing is we're going to set up our eigenvalue buckling solution. So I'm going to leave the analysis. I'm going to change the modes to 3. I'll talk about that. I'll talk about that or why in a second. And we're going to leave our pre-stress to pre-stress environment static structural. I'm going to right-click insert deformation total. I'm going to do this 3 times. So we have 3 modes that were buckling modes. On the second one, I'm going to change the mode to 2. On the third one, I'll change the mode to 3. Okay, now we're all set. So I'm going to right-click solution and click solve. And there's our eigenvalues. First one is a load multiplier 54.729. So if we want to look at these modes, I'm going to orientate the part so that we're viewing the YZ plane. And this first mode is going to rotate. You'll see it's going to look like it's bending about the x-axis. And you can actually animate this by coming down here and clicking play. So we can see that's our first mode. And our second mode, so I'll talk about this in the next video, but the second mode is actually a based on a fixed constraint mode. And I'll talk about that why in the next video. But essentially, this is the first mode if we had fixed boundary conditions, because the rotation about the z direction is fixed. So we're getting kind of a mixed mode result here, which is what I expected. And then the classical second mode for the pinned orientation is shown here. And you see here that these two are basically identical, and that checks out with the hand calc. But yeah, thanks for watching, and hopefully you guys stick around for the next video.